So thanks to Lemma 1.5.10, now we can introduce the unique divisor of a Weil differential. And we can also consider for this unique divisor, or the divisor of the Weil differential, we can also consider its valuations. In other words, we will introduce the divisor, and indeed on purpose at the moment it's not clear, but on purpose we are going to denote like a principal divisor of a function. Indeed it will be the case, but for the moment it will be enough to treat it as just a divisor of a given Weil differential, non-zero Weil differential, as the uniquely determined divisor of the function field, which satisfies two properties. The first one is this non-zero Weil differential vanishes on the other space of this divisor plus f, and if w vanishes on the other space of some divisor a plus f, then a is always less than or equal to this divisor omega with respect to partial order in the divisor group. And when we consider this divisor, so that means the divisor of a given non-zero differential, we will define valuation of this differential in terms of the valuation of its divisor. And like in the functions, we can also investigate their zeros and poles by checking if the discrete valuation has strictly positive or negative value. And indeed we will say that the Weil differential omega is regular at given place P or given point P if its valuation is always bigger than or equal to 0. And in general, we call omega regular, or you may also come across the keyword as holomorphic if omega is regular at every place P. And finally, we will define the canonical divisor is the divisor of some Weil differential omega. And indeed, with respect to this definition, let me note that we can treat the Weil differentials of the divisor A, so that means these are the differentials vanishing on the Adel space of A plus F. We can say that this can be zero differential, or its divisor is bigger than or equal to A, because this omega will be in some sense the maximal of the set of the divisors of a Weil differential, fixed Weil differential omega. And indeed, with this interpretation, if we consider all Weil differentials such that these are positive, so that means for each P, they are regular. By the definition of the index of specialty, indeed, we can say that the space of regular Weil differentials, the dimension of the space of the regular Weil differentials, gives us another interpretation of the genus of the function field F. And now we want to see that. So how, for instance, we have seen that for a given Weil differential, we consider its divisor, and we also have seen that XW also forms a Weil differential. So because we have seen that the space of Weil differentials forms a vector space over the function field, and now we want to understand how its divisor look like. And in proposition 1.5.13, we will answer this question. Indeed, we will see that for non-zero function x and non-zero Weil differential omega, the divisor of the Weil differential x omega is determined by the principal divisor of this function x and the divisor of the non-zero Weil differential omega. And as a consequence of this observation, and due to the property of the Weil differentials forms a vector space over F, one-dimensional vector space over F, we will be able to see that any two canonical divisors of the function field are equivalent. So indeed, we have already observed this fact when we stated the Riemann-Roch theorem, or we stated this fact as a consequence of the Riemann-Roch theorem, but indeed we can also do equivalence with the notions of the differentials. And indeed, this part B tells us that the canonical divisors of the function field forms a class in the class group. So canonical divisors of the function field form a whole class in the class group because of this equivalence. So that means if you consider two canonical divisors, so they are going to be equivalent. So that means they belong to the same equivalence class. And this class indeed is called the canonical class of the function field, and it is useful particularly in the arithmetic algebraic geometry. But for this moment, we want to see that how the divisor of the Weil differential xw look like. Indeed, if you consider a Weil differential w, we know that by the definition 1.5.11a, this is also vanishes on this other space and the other space of its divisor. So that means if W is a Weil differential, which is vanishes on the other space of some divisor A, but particularly also on the other space of its divisor plus F. As we have observed in the beginning of the lecture, we know that xw vanishes on the other space of A plus principal divisor of x plus f, and in particular with the setting, that means xw also vanishes on the other space of the principal divisor of x and the divisor of the Weil differential omega plus f. And again, with the same definition, but part B, part 2, if W vanishes on this space, we know that this divisor is less than or equal to the divisor of the Weil differential. So that means if we apply this second item, if xw vanishes on this space, that means x plus w is less than or equal to the divisor of the Weil differential x omega. And indeed, this shows us this inequality. And in order to see the other side, indeed, it will be enough to replace omega by the Weil differential x omega and the function by x inverse. Indeed, this is nothing but the divisor of the Weil differential omega. And thanks to this inequality, we can see that indeed this divisor is bigger than or equal to the principal divisor of x inverse plus x omega. And since the principal divisor of x inverse is equal to the minus x, indeed, by taking this minus x onto the right-hand side, we can also see that the divisor of the Weil differential x omega is less than or equal to principal divisor of x plus the divisor of the Weil differential of omega. And this shows us the other inequality. And thanks to this two inequalities, we can complete the proof of part A. And to see the equivalence of two canonical divisors, let me choose two canonical divisors, W1 and W2. So that means these are the divisors of some weil differential omega 1 and omega 2. Since the space of weil differentials is a one-dimensional vector space over the function field, we know that this is always possible to consider a function x such that W2 can be written as, W1 can be written as x times W2, or I mean, vice versa. But this means that the divisor of the weil differential W1, this is the divisor of the differential xW2, can be written as the principal divisor of x plus omega 2 from part 1, part A. And indeed, this shows us the equivalence of the canonical divisors W1 and W2.